It's easy to focus just on how strong a storm is, the wind speed, the hail size. But actually, so much of our climate, and especially the really impactful weather, it's driven by something else. It's driven by organization, how these individual storms team up. Today, we're digging into one major example, the mesoscale convective system, or MCS for short. So this is basically a complex of thunderstorms, bigger than one single storm, yeah, but smaller than those huge cyclones we track across continents. Our goal here is simple. Get a quick handle on what they are, the different flavors they come in, and why these systems, which can last for hours and hours, are so incredibly important. But before we dive deep, just a quick word about our sponsor, embersilk.com. If you're looking into AI for education or integrating it into your business, Embersilk is your answer. Really helps you stay ahead. Check them out at embersilk.com. Okay, so MCS. To start us off, can you give us a sense of the scale? How big are we talking, and why should we care so much?
Well, the scale is really the defining feature. An MCS is basically a region of thunderstorms. Could be sort of circular, could be linear, but it has to be at least $100 text kilometers across in one direction, minimum. And why care? Well, if you live anywhere near the U.S. Great Plains, they're absolutely vital.
Yeah, I saw a number in the sources that just, well, it blew me away. About rainfall.
That's right. It's fundamental to the rainfall climatology there. MCS are responsible for about half, somewhere between, say, $30 text and 70 text percent of all the rain during the warm season in the Great Plains.
Wow. Half the rain. That's huge. They must be incredibly efficient water deliverers then.
Highly efficient, yes. And reliable, too, relatively speaking.
So what's the secret sauce? What lets these things hang around for hours when a normal thunderstorm just pops up and dies?
It really boils down to two main ingredients, mechanically speaking. First, you need plenty of moisture. We talk about precipitable water, basically how much water vapor is stacked up in the air column. Usually you need values greater than about 31.8 text millimeters.
Okay, lots of moisture. Got it. What's number two?
Number two, and this is really critical, is significant vertical wind shear. That means the wind speed and direction change noticeably as you go up. We're typically looking for more than 25 docks of shear, just in the lowest $6 text kilometers or so.
And what does that shear do?
It essentially tilts the storm system. This tilt keeps the updraft, the rising air feeding the storm, separate from the downdraft, which is the rain and cool air falling out. In a single cell, the downdraft quickly chokes off the updraft. But with shear, they stay separate, and the storm can keep regenerating itself for, well, hours.
Ah, I see. So the shear provides the organization the longevity. Okay, let's talk types then. The sources mention these like big round ones and then these intense lines.
Exactly. The big, generally round one is called a mesoscale convective complex, or MCC. It's a specific type of MCS defined by satellite imagery. It needs this really large, continuous, cold cloud top shield specifically. Cloud tops colder than 3W2 text covering an area over $100,000 text square kilometers. They last a long time, and interestingly, they tend to be nocturnal. They often form and peak overnight.
Okay, the MCC, nocturnal giants, what about the lines?
That's the squall line. It's the linear cousin, an elongated line of thunderstorms, often quite severe. This is the structure where you often get really strong straight-line winds, sometimes associated with a feature called a bow echo on radar.
Right, I've heard of those nasty winds.
Very nasty. And sometimes within the squall line, you can get a pattern called a line echo wave pattern, or LEWP. Those kinks in the line are often hot spots for tornado development.
So MCCs and squall lines are the big warm season players. But the definition seems broader. The sources mention some, well, unexpected members of the MCS family.
That's true, because the definition hinges on scale and organization, not necessarily warmth. So technically, lake effect snow bands can qualify.
Snow? Really?
Yeah, think about it. Cold air moving over relatively warm lake water creates instability and rising motion organized into bands. It's convection on a mesoscale. And if the instability is really, really high, a huge temperature difference, you can even get thunder snow.
Thunder snow. Wild. Any others?
There are also polar lows. These are like small, short-lived hurricanes, basically. Little low-pressure systems that form over oceans at high latitudes, usually in the cold season. They can pack gale-force winds, again, organize convection on the mesoscale.
It's fascinating how that organizing principle applies across such different phenomena.
Yep.
Okay, but maybe the most mind-bending part is what can happen after an MCS dies. This MCV thing.
Ah, yes. The mesoscale convective vortex, the MCV. It's essentially the leftover spin. Once the thunderstorms in the MCS weaken and dissipate, you can be left with this persistent circulation, this sort of low-pressure area, mainly in the middle levels of the atmosphere. It's like the ghost of the storm system.
An orphan swirl, as the source put it.
Yeah.
And that swirl, It sticks around.
It can, yes. That's the remarkable part. An MCV can maintain its identity for several days, just drifting along with the larger atmospheric flow.
And what happens then? Does it just fade away?
Sometimes. But sometimes it becomes the seed for something new. It can drift into an area with favorable conditions, maybe hundreds of miles away, and provide the necessary spin to kick off a whole new round of thunderstorms.
Wow.
Or, and this is really fascinating, if that MCV drifts off the continent and moves over warm tropical waters.
Wait, don't tell me.
Yep. It can actually provide the nucleus, the initial spin needed for a tropical storm or even a hurricane to develop.
No way. So a thunderstorm complex over, say, the Midwest could eventually lead to a hurricane.
Absolutely. Hurricane Barry back in 2019 is a prime example. It originally started as an MCV that formed over the U.S. mainland, drifted into the Gulf of Mexico, and then spun up into a hurricane.
That is incredible. The idea that the rotational memory of a storm complex can survive, travel, and then seed something as powerful as a hurricane, it really changes how you think about the atmosphere.
It highlights the interconnectedness, the transfer of energy and momentum over vast distances and timescales.
So if the remnants of a dying storm complex can travel maybe hundreds of miles to seed a hurricane, what does that tell us about the hidden continuity of energy transfer in our atmosphere? Definitely something to think about next time you watch a big storm system fade out on the radar. Well, that's all the time we have for this deep dive. Thanks so much for joining us and getting intellectually curious about these amazing atmospheric systems. If you enjoyed this, please do subscribe wherever you get your podcasts and maybe leave us a 5-star review. It honestly really helps us out a lot. Thanks again for listening.